Hi everyone. Today in lecture 5, we will discuss our first lecture on torsion. Before talking about the torsion, let me give you the recap for the entire axial loading chapter, because when I give you the lectures on torsion, I'm gonna make a sort of one-to-one correspondence between axial loading and torsional loading, and you're gonna find like a much better way and much easier way to understand torsion if you start to have the mapping between axial loading and torsional loading in mathematical formulations. Okay, so we begin our discussion on axial loading by defining what is axial loading, right? So I told you that given like a complex force and torque combination, we can make an imaginary cut in any part of the beam or pillar, whatever you call it. And if you define two forces N and V and two torque T and M with respect to the centroid, then you can always make a mechanical equilibrium. And out of those four reactions, two forces and two torque, if only n is non-zero and all the other reaction turns out to be zero, we call that as axial loading. So one of the example we considered was this example, which is axial loading, and this example, which was not axial loading, right? After making the definition of axial loading, we move on to the definition of ductile and brittle material, and I gave you some representative stress strain curves for ductile and brittle material. And please remember the definition of elastic regime and yield stress, ultimate strength, and etc. And I now expect you to have a distinction between strong and stiff, and between stiff and tough, and between strong and tough. Okay, so as a mechanical engineer, when you talk about these three words, please make a distinction clearly from now on. After we discussed about ductile and brittle material, we move on to how to obtain displacement under axial loading. So when you want this obtain displacement under axial loading, you have to obtain force P and length L and the cross-sectional area A and Young's modulus E. Okay, so as a combination of this P, L, A, E, you can obtain the displacement delta. Having discussed about displacement under axial loading, we move on to the problem on static indeterminacy. What I mean by static indeterminacy is the problem that I cannot obtain the solution. I cannot determine the force and stress state only with statics. Okay, so because we cannot solve the problem with statics only, I mean freshman physics only, we have to think about the constraint on deformation, and then we can obtain the additional equation and we can solve the problem. Okay, and when we make a discussion on static indeterminacy, we talk about superposition principle. So I also told you that we can either decompose volume or we can decompose forces to solve the problem. So under the linear response problem, like for example for solid mechanics, if we stay in the linear elastic regime, then we can solve the problem by decomposing the problem into either volume and forces, and the solution of each decomposition problem and summing up those solutions, and I told you that we can then reproduce the solution of original problem, right? Then we move on to the discussion about elastic constants, and we have a discussion on what's the meaning of Young's modulus, Poisson ratio, and shear modulus and bulk modulus, and we also derived the relationship between these four. Okay, and because of these relationship, out of four, only two elastic constants are independent. In addition to that, starting from this relationship, I told you that the Poisson ratio should be larger than -1 and smaller than half. Okay, then we move on to Saint Venant's principle, because as I told you, we can make a force on this little tip. We can make a force with like circular object, or we can make a force with this kind of plate. Okay, but whatever geometry you are using for making the force, in the end, when x is larger than the width b, then stress distribution becomes uniform, and we don't need to worry about how we exactly apply the force at the end. Okay, and this is why we typically get high aspect ratio problems in our textbook, because for high aspect ratio problem, yeah, we have quite a large fraction which has like a uniform stress distribution, which is also far from the end of the beam. Okay, that's why we have like a high aspect ratio problems in chapter 1 and chapter 2. Then after discuss about Saint Bernard principle, we discuss about the topic on stress concentration. When we have a hole in the paper, or when we have this interesting shape of the object, stress does not distributed in uniform way. Okay, especially stress near the tip, stress near this joint is much higher than the average stress, and we have the table for or figure for stress concentration factor, and by utilizing stress concentration factor we can obtain the maximum stress, and after obtaining the maximum stress, we have to set our allowable stress must be larger than the maximum stress due to this stress concentration factor. Okay, so these are the topics we have gone through in axial loading chapter, and in torsional loading chapter, yeah, we'll follow like a most identical path when we make a discussion on torsional loading. Okay.